Hello and welcome back to another Dr-Tutor video. Today we're going to be going through the first part of the Modern Analytical Techniques topic for A-Level. This video has been catered more towards the Edexcel Specification, but has been adapted so that it's kind of more broad and can be used for all the major specifications. This will be a slightly shorter video purely because this is quite a small topic in comparison to some of the other topics in the specification. But yeah, let's get into it. So the first part of this topic is mass spectrometry, or mass spec for short. It's used to enable us to determine the MR, or relative molecular mass, of an organic compound through the molecular ion peaks formed by the process. And those molecular ion peaks will appear on a graph of sorts, which we'll see in a few slides. So the process is as follows. A sample element or compound will be injected into the mass spectrometer, and this sample is bombarded with a beam of high energy electrons from an electron gun. The energy from the bombardment of electrons leads to the atom's molecules forming positive ions. So these positive ions then fragment into multiple particles, forming a positive particle and a neutral particle. The positive ions formed are then accelerated using an accelerator plate. This has very high electrical potential. So these ions then pass through slits and emerge as a parallel beam of ions. As all the ions have the same energy, if they have the same mass, they travel at the same speed. The ions are then deflected by a powerful magnetic field. So ions of greater mass but equal charge are deflected less, and ions with lower mass are deflected more. The angle at which the ions are deflected is based on the strength of the magnet and the mass to charge ratio, or M to Z ratio, of the ions. The ions of lowest mass will be detected first, and then the magnetic field will be gradually increased and the ions of higher mass are detected. The detector is linked to a computer which calculates the mass to charge ratio of each positive ion and its relative abundance compared to the most abundant particle, and this is then converted into a percentage for each positive ion, which is used to calculate isotopic mass as an average and is displayed on a mass spectrum graph, which again we'll see in a few slides. The key is that we understand that the smaller and more positively charged fragment ions will be detected first, as they'll be deflected the most and are more attracted to the negative pole of a magnet. Using mass spec, we can get an understanding of the MR of the compound and, to an extent, predict the structure of a simple organic molecule, as we should know the common MR of, say, CH3, 15, or CH4, 16, etc. And we can watch out for peaks at these points on the mass spec and then have an understanding that these common groups are present in the organic compound. It's also important that we understand what an M plus peak is. So this will be the peak with one of the highest values, and for organic compounds you can try and figure out what the structure will be using logical combinations of known values. The M plus peak will also be the MR. Here we see a sample mass spec with the mass charge ratios on the bottom of the graph, and we can also see the highlighted M plus peak. The second part of this topic is infrared spectroscopy, or IR spectroscopy for short. So IR spectroscopy is a technique used to identify compounds based on changes in the vibrations of atoms when they absorb infrared of given frequencies. So the sample will be exposed to electromagnetic waves in the infrared region, and then a sensor will detect the intensity of the wavelength of the infrared radiation which goes through the sample. So all organic molecules absorb infrared radiation, and depending on which energies of radiation are absorbed, the bonds between atoms will vibrate by either stretching, bending, or twisting. The molecules will only vibrate at a specific frequency, and this is called the resonance frequency. The rest of the molecule also has an impact on the way in which each vibration absorbs a specific wavelength of infrared radiation. So even though a given bond might be the same, it may appear different on an infrared spectroscopy graph. For example, the OH bond in an alcohol appears completely differently to the OH bond of a carboxylic acid. So infrared spectroscopy has to be used in conjunction with mass spectrometry to determine the rest of the structure. There'll also always be a fingerprint region below the 1500 wave number region, and this fingerprint region is unique to a specific molecule in the same way that our fingerprint is unique to us as individuals. You won't need to be able to identify fingerprint regions, but they're useful in kind of like a lab setting for identifying structures. So this slide shows an example infrared spectroscopy graph. We can see that each of the regions is labeled, and it's worth learning the approximate region and shape of a peak and what bond that correlates to, although you will be given a data book which will show you the wave number ranges for each peak in your exam. But other than that, this more or less covers the topic. We've covered mass spec and infrared spectroscopy, which are the two main regions for part 1 of the topic. There will be a video coming out shortly on part 2, which goes into a lot more detail, and that's what you'll really be asked questions on in your exams. As usual, if you want detailed notes, you can head over to dr-tutor.co.uk, and there you can also book one-on-one tutoring where we'll go over personal questions, go over the entire topic in proper detail, cater to your spec as opposed to kind of like the broad brush technique used in videos. And there's also a whole heap of useful resources if you're applying to medical school. But thank you for watching, and I hope you found the video useful.